At the end of the previous video, we defined a new mathematical structure, a new geometrical structure, which was that of Riemannian or pseudo-Riemannian space, by defining an additional structure over a differentiable manifold. That additional structure was the metric. In this video, we are going to discuss a completely different structure. In principle, it is conceptually independent of the metric, which is called the connection, and which is something that you can define on differentiable manifolds. In the case of the metric, the reason for defining a metric was the need to measure distances, and then from distances, areas, volumes, etc. In this case, the concept of connection answers to the question of parallelism. You are used to the concept of parallelism in R3, well, and by extension to Rn. And if you have two vectors in Rn, what you do to say if they are parallel or not is that you just parallel transport one of them to the origin of the other, so they have the same origin. Okay. And okay, if they are superposed, when they share the same origin, then you say they are parallel. This would mean, if they are parallel, if there is some real number, positive real number, such that V is equal to AW. In this operation, well, you see no mystery at all, and that is because there is no real notion of vector defined at a point. In Rn, it doesn't matter where the vector is defined. However, in differentiable manifolds, we have emphasized that vectors are defined at a point. Vector fields are defined at all points, but they are not vectors, they are vector fields. They are rules that assign a vector to each point. So we really have different vector spaces at different points. We drew this kind of picture. So this is our differentiable manifold. So this is a potato, okay? And if you have a point P here and a point P prime here, vectors can be visualized as, well, here it is a plane tangent to this surface. In general, it's just a vector space. The idea that a vector space, two-dimensional vector space, which is attached to a point, coincides with this vector tangent to this potato surface at the point P. But in general, you cannot have this visualization, okay? But this is just an example, but the idea is clear. So you have vectors which are defined in this Rn, okay? In this case, it is R squared, and it makes sense to say if two vectors here are parallel or not. And if I have a vector somewhere else, okay, I just parallel transport it to P, to the origin, and that's it. The same I can do here. Let me call this P prime Q, because I think it is a bit better not to use primes. Then I have vectors here. Well, there is really no problem in defining if two vectors in this particular vector space are parallel or not. I just apply this rule. It is R squared. However, I cannot say easily if a vector here, let me call it psi p, is parallel or not to another vector here. Let me call it eta q. Why? Well, there is no rule to I can only compare vectors which belong to the same vector space. So how can I compare these two vectors and say if they are parallel or not? Well, I have to invent something, some sort of parallel transport that generalizes this idea that I can move a vector from one point to another, keeping it parallel to itself. And so I transport this vector psi p using this rule, which will be some linear map, okay, and I call gamma, capital gamma, and using this linear map, I get another vector here, but this is another vector, okay? So let me this. This is really another vector in this second tangent space, the second vector space. And now I ask the question whether this eta q and gamma psi of p, which belongs to the tangent space T at q, if this space is M, so this would be the tangent space Tp of M. I think I introduced this notation before. And this question now makes sense. The question is, what is this rule that allows us to parallel transport a vector from the tangent space at P and to the tangent space at Q? If we have this rule, we have to have this rule for every point in space. We will have something which is defined at all points, okay? And since we are doing differential geometry, this rule will define actually the parallel transport from a point P at the point X to a nearby point X plus delta X, okay, infinitesimally close to it. Okay, this gamma, okay, which will be a field, will be an object with 3 indices, and this is the connection. In fact, it's called this kind of connection because there are other connections like the Young-Mills connection or gauge connection and so on. Is called the affine connection. Okay, so now suppose that this Q is really a point which is infinitesimally close to P. Okay, so we have delta x mu, P and Q belong to the same coordinate patch. I will not draw it because it will become a mess. Okay, so consider these points P and Q very close one to each other and belonging to the same coordinate patch, so I can compute this difference between the coordinates of one and the other, and at some point it will be just infinitesimal. Okay, then what I do is to define this parallel transported gamma of psi p. Okay, if you want, well, it's a vector. Let me write the index for the components. Okay, maybe you want to write this in this way because it will be a vector now defined at Q, and we define it to be the vector at P minus delta x rho gamma rho sigma mu. Now you see that once we have contracted these two indices rho, this is something with only two indices sigma and mu, so it is a matrix which acts linearly on vectors. So this is the thing that acts on the components psi sigma of P. Now let us rewrite this in a way in which it is manifest that this is the linear transformation we had promised. So we can rewrite this psi mu as delta times psi mu, and this expression, everything multiplying psi sigma p. Okay, and this is an infinitesimal, a matrix which is infinitesimally close to the identity matrix. This is the infinitesimal transformation. It makes explicit the fact that, of course, this transformation depends on the distance. It is 0, so it is the unit matrix when you don't, the point P is the same point as the point Q. And let me frame this because this is a very important definition of what is meant by parallel transport. And here we have to emphasize that this is a purely arbitrary definition that satisfies certain properties. For instance, it coincides with the notion of parallel transport that you have in Rn. In Rn, this connection just vanishes and you move vectors parallel to themselves. Just you consider that they are defined at any arbitrary point, so no matter what p and q are, psi mu and psi at q and psi mu at p are the same. They have the same components. So this is good, but there is an arbitrariness which is quite large because the connection gamma is arbitrary. There are many of them. If there was a single connection selected by some particular property, then there would be a canonical notion of what parallel transport is, but that is not the case. There is an infinite number of possible connections that one can define, and this is something that we have to deal with later. Now we can consider what happens with vector fields. Vector fields are defined at every point in our differentiable manifold, and the components are given by functions of x that tell you what the components of the vector are at a given point. So if I have 2 points which are very close to each other, the points p and q, I can use these functions to find vectors which are defined at p and q. Okay, just evaluate these functions at the values of the coordinates of the points p and q. Of course, I can do this for the infinite points of my differentiable manifold. But then I can ask this question: if this is the point P and the point Q, which I imagine they are infinitesimally close, and this is psi mu of Q, and this is psi mu of P, and remember that these vectors are given by the definition of the vector field. I can try to ask how much this vector field changes from P to Q according to its own definition. Okay. In order to do this, I have to subtract psi mu Q from psi mu P from psi mu Q. But this I can only do if they are vectors really of the same vector space. So the idea is that I parallel transport this psi mu of P to Q. Let me call it psi mu prime at Q, and then I can subtract psi mu prime from psi mu Q. This would be the way to see how this field varies when you go from x to some nearby point. And this is a previous step to define a derivative. I cannot define it in any other way, because if I want to define a derivative in the standard sense, there is a quotient of infinitesimal increments in the most pedestrian definition. So how do I define an increment of a vector? If I have to subtract vectors that belong to different vector spaces, I cannot do it. So the best that I can do is find the increment between vectors which belong to the same vector space but which have different meanings. This has been obtained directly from psi mu of x, and this one has been obtained by gamma acting on psi. So let us compute this variation. We are going to call the coordinates of the point P in this coordinate patch x mu. P is a generic point and x mu are generic coordinates. Then the coordinates of the point Q, which is infinitesimally closed, will be called x prime mu, and since they are infinitesimally closed, then they are equal to x mu plus some difference which we will understand as infinitesimal. Okay, then the field evaluated, the components of the field evaluated at P will be just xi mu of x, and the coordinates of the field evaluated at Q will be x mu of x prime. Okay, now this is what we called psi mu of q, and this is psi mu of p, and now we parallel transport it according to the above rule, and we obtain a new vector field which is psi prime and which is defined at x prime. Okay, so these are the components, and according to the above rule they are given by the original vector. Okay, remember that this is just psi mu p and minus delta x nu gamma nu rho mu evaluated at psi rho of x. Okay, about this, okay, we know that this is just x plus delta x, and we can expand in a Taylor series, so this would be psi mu of x plus delta x nu partial nu psi mu of x, and these are the two quantities, okay, this one and this one, that we want to compare. Now the difference that we want to compute is psi mu at q minus psi mu prime at q. Okay, this is psi mu prime at q, and this is psi mu q. So I just copy this expression here. Okay. And I subtract this expression here. These two terms cancel, and what we get is proportional, as we might have expected, to delta x nu. Everything evaluated at x, so I'm not going to write the argument. Okay. And this, by definition, is delta x nu nabla nu psi mu. This defines the covariant derivative of psi nu. Of the vector field observe that we cannot compute a covariant derivative or any kind of derivative of just a vector at a point. You need something that varies over the geometrical space. Another thing which is implicit in this definition of covariant derivative is that it is with respect to certain connection. So sometimes we need to mention it, and some other times it is understood that this covariant derivative is the covariant derivative with respect to the affine connection gamma. There could be some other connections. Okay, so gamma is implicit, and now you have this increment that we can compute. There is this increment, and clearly this can be understood as sort of the quotient, okay, between these two things. It is really the coefficient of proportionality between these two increments, and this is, well, what you understand as a derivative. Okay, another why do we call this covariant derivative? Okay, it is called covariant because it transforms covariantly, in the sense that if psi mu is a tensor, in this case it is a contravariant vector, delta nu of psi mu is a 1,1 tensor. This is one time contravariant and one time covariant. The name covariant derivative makes you think that this is the only covariant derivative that one can define. This is wrong. There are other derivatives that one can define which are also covariant in the sense that they transform tensors into other tensors. These are the exterior derivative and the lead derivative that we will not see in this course. You will have to attend the advanced course. Okay, the reason why this should be a tensor is because the procedure by which we have defined this point by point is a procedure that is guaranteed to transform tensors into another tensor. You see that here the parallel transport, we said that it should be such, so this connection should transform in such a way that transforms a vector at this point into a vector at the other point. Then we are subtracting vectors. This gives you another vector, and this delta xi nu is just a number, a set of numbers. This is nothing else. So you expect this to be really to transform as a tensor, because it is the result of allowed operations between tensors. Now, since this is what we expect, and this follows from a property of gamma that we announced that it has to have, the transformation properties of gamma under coordinate transformations, then we have to find that transformation rule. The best way to do it, instead of trying to find how gamma has to transform in order to transform vector fields into vector fields, is to see how gamma has to transform in order for this covariant derivative that we just defined is a tensor. So it transforms covariantly. Let's see how the covariant derivative transforms under general coordinate transformations. We want to study the transformation of nabla mu psi nu, and remember that under general coordinate transformations, a contravariant vector, the components of a contravariant vector, transform in this way. Okay, as for the partial derivative, okay, if we add a prime just to indicate that this is the partial derivative with respect to the new coordinates y nu, they transform in this way. Okay, so first of all, observe that if we had tried to define a derivative on tensors, in particular the contravariant vectors of this form, which is the most naive derivative that you can construct. Okay, it is a derivative, but it does not transform the vector xi into a 1,1 tensor, one index up and one index down, because this does not transform as a tensor. Let's see how it transforms. We have partial prime nu, psi prime nu, and before I apply these two rules, let me rewrite them using the Jacobian matrix, which is this one. So this would be J mu nu, and then this would be the inverse Jacobian matrix J minus 1 rho nu. So I have J minus 1, but I have to adapt the indices because here the free index is mu, and let me use alpha. So this transforms in this way, and then psi prime nu would be the free index nu would be here, and then we call this beta psi beta. Now I am going to operate, but first this partial derivative will act on psi and then on the Jacobian matrix, and I just reshuffle a bit the terms. Okay, I get partial alpha psi beta I minus 1 alpha mu, and this first term is clearly the first term that you obtain if this was a tensor, a 1,1 tensor with which transforms contravariantly with respect to the upper index, which here is nu, and one time covariantly with respect to the lower index, which here is mu. But there is another term. Okay, so This changes a bit the situation. And the other term is plus this factor stays there, j minus 1 alpha mu, and then there is partial alpha j nu beta psi beta. Okay, this term is not a term that should appear in the transformation of a tensor. This term is an inhomogeneous term. In the transformation. Okay, it does not depend on the tensor itself, which is partial of psi, but a would-be tensor, because the conclusion is that the presence of this term makes this not a tensor. So this is not a tensor. So this is not a covariant derivative. The partial derivative is not a covariant derivative, except in the case in which it acts on a function or a scalar. But in general, it is not. And this is, well, the reason why there is this additional term here, precisely. The mission of that term is to cancel this inhomogeneous term. But it also has to transform with the appropriate Jacobian matrices. So basically what we want is that nabla prime mu psi prime mu, which is partial prime mu psi mu plus gamma mu rho nu prime psi prime rho. This should be equal to just this term here with the partial derivative replaced by nabla. This is the definition of a 1,1 tensor transformation. Okay, now we know what this is because we have it here. So let me write it. This extra term here, alpha mu partial alpha j nu beta psi beta, and then this term, which we still don't know, and this is equal to this term here, and then put it here. This is j minus 1, sorry, j nu beta partial alpha psi beta plus gamma alpha gamma beta psi gamma, and j minus 1 alpha mu. So compare these two sides, you see that this term is right here. This is the one that we want. But now the transformation of this term has to give this one and has to cancel this one. Okay, let me put this and as an equation. This transformation has to be, gamma prime psi prime rho has to be alpha gamma beta psi gamma j minus 1 alpha mu minus j minus 1 alpha mu partial alpha j nu beta psi beta. Okay, let's add another piece of information, the fact that we know what psi prime rho is. So this is equal to gamma prime mu rho nu j rho, and here I'm going to choose gamma. Okay, so I think I will change this beta by gamma. Okay, gamma psi gamma, and equal to all this. But okay, observe that because I have written it this way, I can put everything in brackets, and take gamma here. Okay, so now clearly this coefficient must be equal to this expression in brackets. Okay, and the next thing that I'm going to do, so let me eliminate this. This has to be is equal to this, and just eliminating psi gamma, you have that this is equal to this expression in brackets. Okay, so the last thing that we need to do is to multiply both terms of this equation by j minus 1 gamma and then for instance sigma. Okay, this gives gamma prime mu sigma nu, and here we have j nu beta gamma alpha gamma beta j minus 1 alpha mu j minus 1 gamma sigma. Okay, this could be the whole transformation if this was if gamma was a tensor, but then there is the second term j minus 1 alpha mu partial alpha j nu gamma and j minus 1 gamma sigma. Okay, just to put everything together, this is gamma sigma nu prime, and now that we have the complete result, let me put it into a box. Okay, this is the full expression. There is a small simplification that you can do in this formula using this property. If I take the partial derivative, the indices do not matter here, of j minus 1, this is just minus j minus 1 dj j minus 1 in this order. These are matrices, they do not commute, so the standard thing that partial x minus 1 is minus 1 over x squared is not possible here. I cannot put these two j minus 1s in the first place. The fact that this is true, you can prove using that this is equal to 0. So this is dj minus 1j plus dj, plus j minus 1 dj, and now you multiply both sides of this equation by j minus 1, and you get that the j minus 1 plus j minus 1 dj j minus 1 is equal to 0, which is the equation that you have here. Okay, so how do I apply this? Here I have basically the j minus 1. Okay, these two indices are contracted exactly as you expect in the product of two matrices. So if I start from this expression here, I would multiply this by j. Okay, both sides, I get this. Let me remove all these formulae that we do not need in the blackboard. Okay, and now I can go here and replace this expression, okay, including the minus sign, by j nu gamma partial alpha j minus 1 gamma sigma, and the thing that stays in principle the same is this j minus 1 alpha mu, so this will be with a plus. About the indices, if you are a bit mystified by the way I have done this, consider that this expression in principle has this product of matrices has two free indices, nu and sigma. Okay, so mu and sigma are here, and then there is another index in between, which is the index you sum over when you multiply matrices. The first index corresponds to the first matrix, so here this corresponds to J nu. Then there is the internal index, which here is gamma. Okay, the partial derivative with whatever index, then J minus 1, since it is multiplied by J, then really comes with the gamma index, and then the last index corresponds to the second matrix. So this is equal to partial, and I do here exactly the same, J minus 1 gamma sigma. This is what I have done here. Okay, the last step in this simplification is to realize that this J minus 1 alpha mu is partial x alpha with respect to y mu, and that in this expression this partial alpha is actually partial x alpha. So using the chain rule, all this becomes plus J nu gamma partial y mu J minus 1 gamma sigma. Okay, this is a particular way of writing it, which I think it is easier to remember. That at some point, when you study Young-Mills fields, you will be able to relate to this expression. Okay, so let me summarize. This is the result. Remember that okay, this expression should be entirely replaced by this, or can be replaced by this if you want to write it in a slightly more simplified form, and that in all this game, J mu nu, the Jacobian matrix, is by definition, partial y mu with respect to x nu. The inverse matrix is partial x mu with respect to y mu. So summarizing, we have obtained this non-tensorial transformation rule for the connection. As we advance, this will allow us to set to zero all the components at a given point, but only the components and at that point, and not the derivatives of gamma. This is an important thing. Okay. We will see this in a bit more detail. Probably you will see this in much more detail in the advanced course. Now remember that this gamma will be the gamma that also appears in the laws of motion and represents inertia. Okay, so this property that it can be set to zero fits perfectly with all the pictures that we were deducing from the equivalence principle. Now that we have defined this covariant derivative, we have done it only for contravariant vectors, but we can extend it to more general fields. So, for instance, for scalar fields or functions, this covariant derivative is just the partial derivative. Okay, you can just see by using the chain rule that the partial derivative of a scalar is a covariant vector field or a one form. So it is covariant. This would be the first extension. Then another property that we want from this derivative is that it satisfies what is called the Leibniz rule. So the derivative of the product of two tensors, t and s, could be the covariant derivative of t times s plus t, the covariant derivative of s, for any two tensors of any given rank or any ranks. Then the consequence of this definition is that if you take the covariant derivative of the product or the contraction of one form and a vector, which is a function, Okay, you have using this property that this has to be this. I add the parentheses for clarity, but in general, when I read something like this, it is understood that this operator acts on the first term on the right and not on the rest. Okay, so I don't really need these parentheses. Okay, this is because of the Leibniz rule. This I know what it is. So I knew, and this is partial mu psi nu plus gamma mu rho nu psi rho. Okay, so now I eliminate the parentheses. Let me write this in this form. This is partial mu of omega nu psi nu minus partial mu omega nu psi nu plus omega nu gamma mu rho nu psi rho. Now this is a function, so using the property I, this is just partial mu of omega nu psi nu, which is the term that I have here. This means that all the other terms should add up to 0. So I have now the mu omega nu minus partial mu omega nu plus omega nu gamma mu rho nu, and I have to do something in order to get to write psi as a common factor. So I change this index by rho, and the other terms, the terms which are different from this, should be 0. This is equivalent to this equation, and this is true for any one form and any vector psi. So this must be true. This coefficient have to be 0 always. This means that this is equal to this minus mu rho nu, and this is the covariant derivative on a one form. The order in which I have written omega and gamma here is, well, conventional. These are numbers. I can put them in any order. These are not numbers. This is an operator, and this is a number, but I cannot write them in any other that the operator is acting on the numbers. This is completely arbitrary. Okay, but there is something to remember as a general rule. Okay, you can write this in this way. When you have covariant tensors, in general, you get minus signs where you have plus signs for contravariant, and this kind of contraction instead of gamma acting on psi with a lower index and upper index in this order, you have a lower index first from the form and then the upper index of gamma. It's a kind of mnemonic rule. Okay, if this is true for these tensors, and this means that using the transformation rule that we have found for gamma before, and the transformation rule for one form, this operator transforms, the covariant derivative of this one form transforms as a 0,2 tensor. Automatically, I don't have to do anything. Okay, now you can extend this to general tensors. So you have a tensor of rank R, S. You have always the partial derivative. Okay, I don't write all the indices, then you get a plus gamma, then first the same index that you have in the partial derivative and here, then a mute index, one that you are going to sum over, say rho, and then the first contravariant index mu is replaced by rho, and mu 1 comes here, then you get mu 2 and so on, and these are untouched. And you repeat the same thing for every contravariant index. And so on. Okay, and then you get minus, let me put it in this order, okay. Well, I said it doesn't really matter. This is going to be now the mute index. This index we are going to sum over. So we have mu s, and then gamma. Always the first index of gamma will be the one of the derivative here. Next is the index we are replacing and the mute index, and you do the same for all the covariant indices. So these are untouched. Mu 1, now it is the turn of mu 2 to be replaced by rho, then mu 3, mu s, again mu, the index you have replaced, rho, and so on. And this would be the general formula for the covariant derivative of an arbitrary tensor. Okay, so the main example that you will see is the covariant derivative of, for instance, of a vector. Well, you have seen already this, if it is covariant or contravariant. So next is the covariant derivative of the metric. This is a very important example. And according to this rule, you have first the partial derivative, and then only terms with minus sign associated to g. So first I replace the index nu by something else that I'm going to sum over, and I have sigma, the index of the derivative, and then the index that I am replacing. And now I do the same for the second index, rho. So it is g nu sigma mu rho sigma. This would be the covariant derivative of the metric. And well, you can use the metric to lower the index, but let's say that we don't usually do that. You don't get many expressions with g multiplying the connection, and in fact you don't get many expressions in which the covariant derivative acts on the metric because of a property that we'll see later on. Okay, you could ask what is now the covariant derivative of gamma itself, but this doesn't make much sense. I could formally treat this as a tensor, as a 1,2 tensor, and add a term with a plus with respect to this index and two negative terms with respect to these two indices. But the truth is that since gamma is not a tensor, really, a covariant derivative doesn't make any sense, because this is not going to transform tensors into tensors. Okay, it's going to transform a no tensor into whatever it is. Certainly not a connection, because although this transformation law that we discovered before, okay, is not tensorial, it is a bit more than that. It's really characteristic of connections. So, but this is for an affine connection, but you will see the same for Yang-Mills connections. Okay. There are other notions that I think I mentioned of derivatives, which are covariant in the sense that they transform tensors into tensors, and that we are not going to discuss very much. Probably we will talk about the exterior derivatives, maybe in as an exercise. It transforms p forms into p plus 1 forms. So it's a very peculiar kind of covariant derivative. It is, in fact, a derivative that does not use any connections. You don't need that in order to transform tensors into tensors, but that is because you are restricted to the particular case of differential forms. So it transforms differential forms into differential forms of a rank 1 unit higher without a connection. Another derivative which is covariant in the sense that it transforms tensors into tensors. Now they are arbitrary tensors into tensors of the same rank. The rank is not changed by this derivative, which is the Lie derivative. It doesn't need a connection either, and it also plays a very important role when we study symmetries. But I think we will see that in the advanced course.